All right, Algebra 2 people. Welcome to the notes for 7.6. This is actually the last new thing we're going to go over in Algebra 2 this year. What we're going to do tomorrow is kind of put it all together and bring back some of the graphing and start matching it all up. Okay, so today we're going to talk about how do you find the equation for oblique asymptotes. So first of all, let's make sure we know when these things exist. Okay, so you find oblique or slant asymptotes when there is no horizontal asymptote. Okay, you cannot have them at the same time. And when there's no horizontal asymptote is when your rational has its highest degree on top. Okay, so the biggest exponent will be on top, and the bottom is kind of worthless as you approach infinity. Okay, by contrast, so that's the slant asymptote. By contrast, the horizontal asymptote shows up in two different cases. When your highest degree is on the bottom and you've got meh on top. Meh could be just about anything as long as it's not a highest degree. Or when your highest degree is tied on top and bottom. And then the answer is whatever's right in front. Okay, and when your highest degree is on the bottom, that answer is the horizontal asymptote is 0. Okay, the slant asymptote only happens when your highest degree is on top. Otherwise, you have a horizontal asymptote. Okay, so first of all, we're going to observe that there is no horizontal asymptote here. And what we're looking at again, because slant and horizontal asymptotes are looking at the same thing. You're looking at end behavior. What happens when the graph goes further and further left and further right? So right toward infinity on the x, left toward infinity on the x as well, negative infinity. Okay. Horizontal looks at end behavior as well, and that's why they can't exist at the same time. Okay, because as you notice, I'm going to find a visual line that's the slant asymptote, and it's not horizontal. Okay, there is no horizontal asymptote in here. Both the left side and the right side are approaching this slanted line, and that's why it's called a slant asymptote, and it's oblique because oblique means slant. Okay, we're going to do the same thing here. So if you have a horizontal asymptote, there is no slant. If you have a slant, there is no horizontal. You have to have one or the other. Okay, never both, and you always have to have at least one of them. Okay, so visually, that's a steeper slant asymptote compared to this guy, who is not quite as steep. Okay, he's still on a slant. It's just not as steep of a slant. So really steep guy in the middle, and then kind of an average guy on the far side. Okay, and every single one of these has a high degree up on top. You can get them to go negative. Okay, so that also applies to your highest degree. Remember, you want your highest degree on top. Okay, horizontal again doesn't go with oblique or slant asymptotes. But anyway, if you want them to go down, the highest degree has to be negative. There has to be a negative in front of your highest degree, and then they go down instead of up. All of these guys are positive in front of the highest degree, and so all of their slant asymptotes go up. Okay, unlike the horizontal and the asymptote, okay, these guys are all slanting, and that's not a number. That is, in fact, an equation. Okay, that's not a number like, 0, 2, 1/2. Okay, it's an equation. Not only is it an equation, but for the ones we're going to be working with, it's a linear equation. Okay, so there's a linear equation that we are finding, and that will be the answer to what is the slant asymptote, and you will be able to give a linear equation. Okay, so we're going to start in the middle with the middle equation, which matches the middle graph. We're starting in the middle because I'm going to use a technique in here that always works. There's a shortcut, but you can't always use it. And I'm going to show you that on a different one. The technique we're going to use is long division. Some of you are going, yeah, I was good at that. And some of you I know are giving groans. Okay, long division, polynomial long division. And this always works on these. Okay, so if you're not quite sure if you can use the shortcut or not, just default to long division because it always works. Alrighty, before we start wondering if, long division or the shortcut, make sure it's a slant. Make sure that the end behavior is slanting. Okay, and yeah, we can see it from the graph, but check your equation. Make sure the highest degree is on top. If the highest degree is on top, you need to find your slant asymptote. If the highest degree is not on top or it's tied, you don't have a slant asymptote, so there's nothing to find. So don't do this if your highest degree is tied or on the bottom. Okay, so to remind you of how long division works, we're going to put our dividend in there. That's the numerator, the top of the fraction. We're going to put it in underneath our dividing box, and something's missing from the back. We've got x cubed, squared, linear. You're missing the constant, so we're going to fill it in with a +0. We're going to use 0 as our placeholder, kind of like 50, 5, 0. The 0 is the placeholder. Okay, the divisor goes out front. That's the denominator, the bottom of the fraction. Okay, and we are looking at first terms, and you want to make them match. How do you get an x squared to match a 2 and an x cubed? Well, the 2 part's easy. We just times it with a 2. Squared going to cubed, we need another x. We need 2x. So I'm going to go over here and put it above its like term, mainly because it keeps me organized. Do you have to? No, but it does tell me I've only got one more slot of these to fill, so it gives me hope there's an end in sight. Okay, what do you do with that? It distributes back to the divisor. Okay, so that thing you were just using to make a match, you distribute it to every part of it. It's no longer just front terms. Okay, so we've now distributed it to every part and put it underneath. Now what do we do with it? We subtract, and all the parts of it subtract. That subtraction goes through all of this new multiplied stuff. So we have a negative x squared minus 4x squared. That's a negative 5x squared. Okay? Negative 5 minus 2. That's a negative 7. So the easiest place to make a mistake in this is subtracting. Okay, there's 3 terms in the divisor. We kind of want 3 terms to match it, so I'm going to bring down that placeholder, the +0. Okay? And we are back to first terms again. We're going to look at just the first terms. Okay, x squared and this new guy, negative 5x squared. To make them match, well, the x squared already matches. We just need a negative 5. And he's going to go over just the normal numbers. And he will also distribute. He multiplies. This is a multiplying part. So we have negative 5x squared, negative 10x, and negative 5. Okay, and that entire thing subtracts. Okay, so this is the easiest place to make a simple mistake. Okay, negative on that 10x, that's a positive 10x. So negative 7x plus 10x gets us the 3x. Negative on the 5, this is a plus 5. Okay, that thing down there, there's nothing more to bring down. That's the remainder. So our answer, here's the stuff on top. 2x minus 5 was the quotient. That's the answer on top. And then we can add in the remainder, 3x plus 5, over, and go to your divisor, the thing that was originally on the bottom, and he's back on the bottom, x squared plus 2x plus 1. Okay, here's the funny thing about end behavior. You're headed for infinity. Look at the remainder. Your biggest degree is x squared in the bottom. When that goes to infinity and you square infinity and divide it into something, it turns the whole thing into 0. So if we're looking at end behaviors, none of these remainders matter. We're going to skip all the remainders. So you will have remainders, but we're skipping them because we're looking at end behavior. And by the time you reach infinity, adding on a little bitty remainder kind of doesn't matter anymore. Okay, so we had this 2x minus 5, and if you look at it, here's negative 5 down here. And if we go up 2 over 1, there's your slope, rise over run. That's the line. Up 2 over 1, up 2 over 1. You can come back and do backwards, down 2, back 1, down 2, and you can be about right there. So the answer to the division problem, that is your slant asymptote. That's the equation for the line that your graph gets really close to as it goes out to infinity on both ends of the x. Okay, and again, if it's not a slant asymptote, if your highest degree is not on top, don't do this because it's not a slant asymptote. This technique gives you slant asymptotes. If it's a horizontal asymptote, do something else. Next up, shortcut time. We're going to go back to the left side of the notes, and we're going to use the shortcut on this little guy. First of all, again, make sure it's a slant asymptote so you know if you even need to do this, okay? Don't do it if it's a horizontal asymptote. We're going to use synthetic division. Okay, synthetic division is best used if your divisor, that's the denominator, is x plus a number and there's nothing in front of the x. Okay, so the last one we did, x squared, that's not x plus a number. The one we're going to do in a minute after this has a 4 in front of the x. It can also be x minus a number, by the way. But the 4 is a problem. You can get around it, and I'll show you how to get around it. But the easiest ones for the shortcut, there's nothing in front of x. Okay, it is a slant asymptote because the high degree is on top. That means, yes, we have to do something. Okay, we either have to long division or synthetic division. And this guy is actually pretty good for synthetic. Okay, the coefficients, so x squared has a 1, they go in our synthetic box. There's a negative 6 here. And then that back 7 goes in the back. Okay, so the dividend goes in the box, just like it does on a normal long division. Okay, this is the part that people mess up sometimes. You're putting in the opposite. Okay, the reason is on long division, you know how we're like subtracting partway through? That's why we don't need opposites, because the subtraction is taking care of that. Subtraction is an opposite. But over here, we need the opposite because there's no place to subtract in synthetic division. So you need that opposite because you're not subtracting. Okay, the 1 comes down. That's something a lot of people forget. They start timesing in the negative 5 early. No, the 1 comes down. Okay, and then the numbers that are stacked on top of each other, those are adding. And then negative 5 times negative 11, that's 55. And then again, numbers are stacked, we're adding. Okay, so generally this is going to be a 62. If it's not, the universe has done something weird. Alrighty. Now we started with an x squared, an x, and a constant, but we just divided out an x. Okay, so if we had an x squared, but we divided out one of its x's, we've only got a single x left. That makes negative 11 the constant. The last term we got is the remainder. Okay, and remember, we don't play with remainders. We're looking at end behavior. Remainders don't matter when you've hit infinity, so we're basically going to ignore that. So what we've got over here with the x minus 11, that is the linear equation. That's the equation for the line that this thing approaches. So it starts at negative 11, and this is going by 10, so it's really kind of hard to tell where it's starting. And then it's got hidden 1s for up 1 over 1, so up 1 over 1, again and again, there's your rise over run. So it works. All right, looks like a good slant asymptote. Now remember, long division always works. So if you're a little hesitant about can I use synthetic, should I not use synthetic, do I shift it, do I do opposite, what do I do? Remember, long division always works, so you can always fall back on that. Okay, for our last problem, we're going to look at two different methods in a single problem because it has a 4 in front of the x, which means synthetic, but there's a workaround that's not too bad. So first of all, let's make sure it's slant. Highest degree is on top. Yes, it is indeed slant. Okay, long division always works. Synthetic works if you know what you're doing, but this one's not bad. Okay, it's not ideal, but it's not bad. Okay, we're going to start though with long division because for those of you who are like, can I just take a method and use it? Yes, the long division method works every single time you have to do this. You only have to do this when there's the highest degree on top. There's a placeholder we're missing, 0x, because 48 is a number, not a linear term. And then 4x minus 32 is going to go outside. You don't have to do opposites to anything. You're just writing them in as they are with an additional placeholder. Okay, now here's a weird part. We need a 4x to turn into an x squared. That's kind of strange. Well, the x part isn't bad. We just need another x. So I know I've got an x at least, but how do you make a 4 turn into a 1? The answer is a multiplicative inverse. We're going to flip the 4 upside down, okay, or find its reciprocal. Okay, so instead of a 4, it's a 1 over 4, because what that does, it turns it into a dividing 4. So when it hits the 4x, 4 divided by 4 is going to cancel, and you'll be left with just the 1. It will also hit the minus 32 because it does distribute. Okay, so we're going to get just x squared, or 1x squared, minus, and then 1/4 hits 32, and that's 8, because the 4 on the bottom is a dividing 4, so 32 divided by 8. Remember that you're going to subtract the group. So the x squareds are gone, and 0 minus a negative 8, those double negatives just canceled. That's a positive 8x down there. Okay, let's bring down the next term, which is a minus 48, and we are just about done with this. This next step is a little bit easier. We need a 4x to match an 8x. And again, you're looking at first terms, okay, just first terms. So how do you get a 4 to multiply up to an 8? Well, probably a 2. That would probably be the best option because the other options aren't going to do that. So 2, and it will distribute, just like the 1/4 did. And we're going to get an 8x, okay, and because you want to match, so you can check yourself as you go to make sure you made a match. And then the 2 times 32, that got us the 64. That group is subtracting, okay, so 8 minus 8, that part's gone. Negative 48, and then you have a minus negative, that just turned the 64 positive. Okay, so that's a 16, negative 48 and positive 64. That's also a remainder. So even though we know what it is, we don't really care. Okay, so this stuff on top, that's the slant asymptote. 1/4 x plus 2. Okay, that's the slant asymptote. And before we go on, let's go ahead and check it against its graph. So 2, okay, that's pretty close to 2. And rise over run, up 1 over 4. So if we go up 1 and then over 4, yep, that's where we would be. And if we find like an actual intersection point, up 1 and then over off the grid 4, yep, that's what it's doing. Okay, so that's the equation for the line that the ends of the graph are approaching, the end behavior. Okay, that's the long division, and it always works. So if you want a method that will always work, there you go. If you would like to try synthetic, okay, it's usually x plus or minus a number, but the problem is the 4. The minus isn't the problem is the 4. You don't want that 4 in synthetic. Synthetic doesn't know what to do with that 4. Okay, so what we're going to do down here, I'm going to show you how to get a workaround for synthetic if you're interested. Okay, but keep in mind, the long division will work. But this workaround isn't bad. Okay, in fact, you've done parts of this already. So here's our equation, x squared minus 48. Now on the bottom, I'm going to factor out that 4. Okay, so we've got a 4x minus 32. That's a group on the bottom. It's actually a group on the top too. That's why nothing's canceling. Okay, but I'm going to pull out the 4, and that leaves behind x minus 8. So see how I basically undistributed the 4, factored out the 4. That's the part I'm going to use. I'm going to use it like the x plus 5 on that far left equation. Okay, but the 4, I'm going to need to remember that there's a 4. It's on the bottom of a fraction. Okay, that makes it a dividing 4, just like the 1/4 we used when we did long division. That's a dividing 4 there. I'm going to need that at the end. But in the meantime, I'm just going to work with the other parts of it. Okay, so x squared minus 48. Well, there's a 1 in front of x squared, but we're missing the 0x term. So we're going to put in a 0 for 0x, and then we have a negative 48 in the back. Okay? And then remember, synthetic does not subtract like division needs to. So subtraction is an opposite thing, so we're going to put the opposite. We're going to put a positive 8 over there. The 4 won't come into it until the very, very, very end. Okay? The 1 just comes down, and then we go 1 times 8. That gives us another 8, and then the stacked numbers add. And then we're going to do 8 times 8. That's a 64. We'll combine it with a negative 48, which should look vaguely familiar, and we're going to get a 16. That's the remainder, and so we're basically going to ignore that. Okay, back to the rest of the problem. See that 4 that we pulled out? That's a dividing 4, and we haven't divided it yet. Okay, so what we're going to do down here with this dividing 4, okay, and we'll fill in the variables too. We have an x squared that went down to an x, but the dividing 4 has to divide into both of them. Okay, so if you have a random dividing 4 there outside of the group you used, you have to divide it into the answer. Okay, so you get 1/4 x, and then 8 divided by 4 is going to be a positive 2. We're skipping the remainder because we're headed for infinity. The remainder doesn't matter. Like, oh, infinity, plus 2, and plus 16 even, doesn't even matter. And hey, look, that's the same answer. So you can get it with synthetic. Synthetic is not a bad way to get this. The workaround isn't bad. You just pull that out, and then you'll divide it into the answer, the final answer, the quotient. Okay? So you can't do it as 4x minus 32, but if you pull the 4 out, you can use the x minus 8 and then throw the 4 back in at the very end. It's almost like slide divide, but without that final slide. Okay? And that's how you work around the number in front of the x if you want to use synthetic. Okay, bonus material time. For those of you who really, really want to know, yes, there is a way synthetic works on things that aren't x plus or minus a number. It's just crazy. So if you're curious, we're going to show you how to do crazy, crazy synthetic. We actually start off the same way. We're going to place all the coefficients. We've got it. And I'm going to make a big box. The reason I'm making a big box is because it's going to be a double-decker box. So we have a 2, and a -1, and a -5, and we're missing the constant out back, so it comes in as a 0 placeholder. Okay, yeah, this is double-decker. The reason it's double-decker is there's 2 things behind our leading bottom x term. Okay, but the 2 still comes down like normal. Okay, we'll worry about the things off to the side in just a second. But the 2 still comes down like normal. And then what happens is it kind of multiplies diagonally. And we'll get our multipliers in a second. But when it does multiply, it's going to multiply diagonally. Okay? And whenever something shows up down at the bottom of the -1 column, it's going to multiply diagonally. Okay? So yeah. And then there is no diagonal at the end. And you'll see why a little bit later. Okay, so let's figure out, what in the world is going on over here. So we're going to use our last example, the x minus 8. You know how it turned into an 8 for synthetic, and then, that was the thing that multiplied every time. You did the opposite. It's the term right after the leading x. So right after our leading x here, there's actually 2 numbers. and we're going to grab opposites. So that 2x, that's going to be a negative 2, okay, without the x. And that positive 1, that's going to be a negative 1. So we're still doing opposites because it doesn't subtract on its own. So we're doing it for it, okay? Whoever's closest to the x squared goes on the bottom. Whoever's furthest back goes in the upper level, okay? And here's how it works. So negative 2 is responsible for all the multipliers on the bottom. Negative 1 is responsible for all the multipliers on the top, okay? So here we go, negative 2 times 2, and we're going to put it right here. That's a negative 4. And there's also a negative 1 times 2, and it goes further up the diagonal. See how it's along that diagonal? Negative 1 times 2 is negative 2, further up the diagonal. Okay, so let's go back into the problem. There's nothing under the negative 1, so it adds to nothing and comes down to the second level, second, sub-basement 2, I don't know, and we're going to add those stacked numbers. That's going to be negative 5, okay? And then we're going to use our multipliers all over again, okay? So our bottom multiplier, negative 2, hits negative 5, and that answers on the bottom as a positive 10. The negative 1 multiplier also hits negative 5 and then diagonals up as a positive 5. Okay, so we've used up our multipliers, so let's get some addition done. Negative 5 plus negative 2, that part is negative 7. And then we've got some more stacked numbers to add. Negative 7 plus 10, that is 3. Okay, now here's why we stop multiplying. Because there's 2 multipliers, but I just ran out of room. So I could try and multiply in the 2, but I really need to be able to multiply both of them. And I cannot, there's no more room to multiply the negative 1. I'm out of top spots. So all multiplying ceases. No more multiplying. So the stacked numbers 0 and 5 add and are just 5, and then 5 has nothing underneath, so he keeps dropping down and is still 5. Okay, that's kind of the answer. So let's look and see how many x's are left to start with. We had x squared dividing into x cubed. That leaves a single x, which makes the negative 5 the constant term. Okay, like there's an x and then there's a number. So 2x and then there's that number, minus 5. And everybody behind that is part of the remainder. Okay, we have kind of an extensive remainder here. Okay, so let's write out the final looking version of the answer. 2x minus 5, and then I'll go ahead and show you what it looks like with the remainder. The start of the remainder actually matches the start of the answer. It's also an x. 3x plus 5, and then it's over the guy that was originally in the bottom. He's still in the bottom, the divisor. X squared plus 2x plus 1. Okay, and you don't really want the remainder for a slant asymptote because we're looking at infinity, and infinity plus 1 is still infinity, kind of. But anyway, if you flip it over and look back to what we got with long division, that's the exact same thing. So there is a way you can use synthetic to simulate long division with a quadratic, or even bigger, x cubed, x to the 4th. You just keep adding levels, okay, and longer diagonals. Okay, x cubed would have 3 levels, x to the 4th would have 4 levels. So there is a way you can do it. It's just really crazy. So anyway, for those of you who are curious, there it is.